Hello. Today I'll explain why high dosages of zinc oxide in the feed are a problem and what solid chemicals approach to solve the problem. Let's start with the pig. It usually eats. By doing so, a part of the feed is of course transformed into meat, which is delicious for us. The bigger part leaves the pig as feces quite fast. The feces serve as manure for plants, among them also plants which re-enter the pig again as feed. This is a nicely closed cycle when everything goes according to plan. But sometimes it does not, and the pig gets sick. The pig gets diarrhea, and the whole feed turns into wet feces with no metabolite actions. In such a condition, the pig does not produce any meat. It might even lose weight. For the plants, this is all fine, but it's a tragedy for the pig. One way to stop this from happening is to throw in some antibiotics into the feed. By eating the antibiotics, the health status of the pig increases. The downside is that there might be some bacteria in the feces or further down the drain. Because the antibiotics are constantly diluted in the environment, they become less deadly for bacteria. The bacteria take advantage of this and adapt, creating antibiotically resistant descendants. Antibiotically resistant bacteria are then a health risk for our own species. When you catch an infection and antibiotics do not help, you still can count on luck. But there is a second remedy to the problem. You just add a large amount of zinc oxide into the feed, sometimes 3 kilograms a ton or more. As a result, the pig is in good shape again. But zinc is a heavy metal and concentrations of 3000 ppm destroy the environment. This is why the regulators usually do not allow this method. From an ethical point of view as well, it is not the way we should treat our environment. So, let's investigate the problem. A good start is to take a look at the place where the problem emerged, in the intestinal tract. Let's take a closer look there. Feed particles from the stomach enter the intestinal tract. Enzymes show up which start cutting the feed particles to even smaller ones. The small particles are then metabolized by the intestines and enter the bloodstream of the animal. The cutting of the enzymes is very crucial in this step. In order to get a better understanding of what happens, let's take an even closer look at the enzymatic reaction within the intestinal tract. There are many enzymes at work here. Each of them operates in a so-called pH window, as indicated here. The pH window is an environment for the enzyme that allows it to work and to cut the feed into pieces. When this environment is too acid or too alkaline, the enzyme does not work. Even when feed particles and enzymes meet up, they do so outside the pH window. The cutting does not take place. This is a real problem in pig production because pigs sometimes change the feed abruptly. In particular, at weaning, the piglets, which are used to mother's milk, will get compound feed all of a sudden. The intestinal tract, which was made to metabolize milk, must now change for compound feed, and this is quite often a problem. It's a problem for human babies as well, by the way. The problem becomes more evident because the enzymes which are now present in the intestinal tract are not able to cut the feed particles down. But somebody else's can. Pathogen bacteria are too happy to grasp this opportunity. They eat the feed which the pig is not able to metabolize. The pig is in a very bad shape. Not only does it not get any energy and therefore is losing weight, it also needs to fight off pathogens. The farmer, seeing the animal's suffering, does not hesitate long and immediately adds antibiotics to the feed. The antibiotics do their magic and kill the pathogens. The piglets usually recover quite fast. But by choosing this path of action, the farmer puts human life at risk. Another remedy involves a very small particle, the hydrogen ion, or just ion for the sake of simplicity. The ion and its buddies are responsible for the acidity of any liquid, and so also for the acidity in the intestinal tract. The more ions, the more acid a liquid. The less of them, the more alkalic. But the ion does not like to be on its own. Whenever the ion gets in touch with a zinc oxide particle, they merge. Other ions join the same particle as well, but only to a certain degree where it's saturated and zinc oxide does not take more of them. The amount of ions is just fine that it creates the local pH window for the most important enzymes. By mere coincidence, it's the same pH window which is necessary for optimal enzymatical reactions. As if it were not enough, it is also the case that the zinc oxide is loved by the enzymes themselves. They attract each other, and above all, in the correct fashion. The active center of the enzyme is now in the vicinity of the zinc oxide particle, but does not lose its ability to cut. The combination of zinc oxide, ions, and the enzymes are a powerful one because it combines the ions and the enzymes in one place at always the best conditions. So when you add zinc oxide to the intestinal tract, the question of whether the intestinal tract is ready to digest the feed becomes irrelevant to you, because whatever the circumstances, it works. What you need to do, thus, is to keep adding zinc oxide, and the conditions in the intestinal tract will be automatically stabilized. But you need to add quite a lot. The concentration of zinc is likely to exceed 3000 ppm, but the amount allowed is only 150 ppm. As you now see, this was the bad solution number 2 which I have presented earlier. But nonetheless, Mother Nature has equipped us with zinc oxide. We should use it. One problem why you need that much is that zinc oxide is a large particle. You can use nanotechnology to either make the particle smaller or to make a large surface. If you do it correctly, you will indeed improve the effectiveness of the particle. Unfortunately, you will not get through the sound barrier of 300 ppm in order to be on the same performance level as 3000 ppm zinc oxide, and you are using some nice technologies just in order to get there. After many years of trial, we finally came across a solution. We found a material which we embedded in the core of an already surface-adapted zinc oxide molecule. The material has no implication on the effectiveness of zinc oxide, but the amount of zinc could be lowered significantly, thus increasing the effectiveness per gram of added zinc oxide. We call it Soldig because it's solid chemicals product and it improves health by digestion. You keep on adding the material into the feed, and you only need 50 ppm for the same effects as before. It is environmentally friendly, and it improves health status by automatically balancing the pH in the intestinal tract. Once the pigs have sound digestion, they can fend for themselves in beating up the pathogens. The antibiotical expenses from the farmers using Soldig went down 75%. The animals grow faster. More feed is transformed into meat. And even for very healthy pigs in laboratory circumstances with feed conversion around 1.2, Soldig reduced the diarrhea index measured by the University of Applied Sciences in Bern by half, compared to positive and negative controls. And all these facts we can support with our large in vitro and in vivo databases. As a farmer, ask your feed mill for Soldig. As a feed mill, discuss opportunities with us. As a pathogen, leave your comment. For the rest of you, like this video. Thank you.